Hi there, IB1s. This is, this is me. I'm doing this a little bit at the last minute because it wasn't until just about now that I found out that we would have to have virtual classes tomorrow. So, as a result, here I am, trying my best to explain what I would explain in class normally. So, what exactly do I have to explain today? Well, today I have to explain the idea of the exponential function. Now, the exponential function is essentially any function that has this kind of a shape. Let me try to write it up as nicely as I can. B times a to the x, and then divided by k, finally plus c. And this right here, this is the general form of a quadratic equation. So, sorry, not a quadratic equation, an exponential function. I need to be careful with what I say here because this is not the same thing. This is very clearly something else. We call this an exponential function for one very simple reason. If we take a look at this function here, and we take a look at this part, we can see that x is in the exponent. It is way up there. It's sitting on top of the a, is in the exponent. As soon as that's the case, as soon as you have an x in the exponent, or whatever variable it is that you're working with in the exponent, well, that's when you know that it's an exponential function. Ergo, I think I'll switch to typeface for this. Exponential function. Okay, so that's kind of our starting point. That's basically what we want in an exponential function. We want a function where x is in the exponent of some number. We don't really care what number, just in some number. Okay, that's fine and well, but now what? Well, what I'm going to try and do today is mainly stick to how do you work with this kind of thing on the GDC. And the reason I'm going to do that is because I don't think it's advisable to do a whole lot else until you are familiar with using the GDC, because more often than not, especially if you see this in a paper too, you're going to want to use the GDC to solve almost any problem that has to do with an exponential function. This is the first thing. And the second thing is to solve it without the GDC requires some more theory that we just haven't got yet. But we will get there, I promise. For now, you will have to content yourself with the calculator as an explanation for it. So let's show it on the calculator. Let's put in some exponential function. Now, how did they look again? Well, we had some number b here, something here that indicated, we'll find out. Let's call it, let's start with just 2 for b. b equals 2. Let's try that. And then let's have a. Let's have a be equal to, actually here we see an interesting problem. What would happen if we set a equal to 1? Well, if we set a equal to 1, then we've got 1 to the x. But does it matter what we take 1 to the power to? If we have 1 times 1, it's still 1. If we have 1 times 1 times 1, it's still 1. Doesn't matter what we make x. If we make it 3, or if we make it 99, or even if we make it minus 99, it's all the same. It's always just going to come back to being 1. So a equals 1 is not really very interesting. Then it would just be a flat line. So we're not going to count that option. A cannot be equal to 1. It has to be equal to something else. Why don't we try 1.5 to start with? Why not? Yes, let's call it that to begin with. And then what about k? Well, let's have k be equal to 2 to start with. Let's try that. And then let's have c be equal to 1. Okay. Seems simple enough. So we have our b first, then we have our a, which I said was 1.5. We take this to the power of x divided by 2, because that was what our k was, right? And we've already put in our a. Oops, that was a little bit ugly. We've already put in our a, and we've also already put in our b. That leaves only this c to be put in. So at the end of all of this, we will say plus 1. Now we see a nice looking, interesting curve. Now, it's a little bit difficult to see much of it at this level of zoom. So why don't we try and zoom out? Why don't we try and zoom a lot out, actually? Do you notice anything interesting already? Is there anything remarkable about the way the graph looks as the x gets smaller and smaller and smaller? As we go further out towards lower and lower x's, what's happening? What is happening to the function? Is it changing a lot as we go out, or is it kind of staying the same? It's kind of staying the same. But what does it approach? What number is it staying the same around? Well, right now I'm at 29, or minus 29. Sorry, my camera's a little bit in the way. But right now I'm at minus 29. What happens if I went to minus 50? Well, I'll try and type it in. Minus 50. I'm at 1. Really? What about minus 75? Still at 1. Wow, what about minus 100? Also still at 1. Basically, what you can see here is that we're getting really close to 1. Does 1 appear in our formula? Well, actually, it does. Have a look at that plus 1. It gets closer and closer to that plus 1, the more negative the x gets. So what we can say here is that this right here, this c, this is what we call an asymptote. Now we'll write that out in capitals because it's quite important. An asymptote. And what is an asymptote? Well, an asymptote has basically two flavors, shall we call it. You have a horizontal asymptote and a vertical asymptote. So if we think about it like this, let me draw a nice function here. If we think about it like this, the vertical asymptote is when a number basically, or when a function gets really close to a specific number, but it doesn't quite touch it. It just keeps going crazy up, basically seemingly as if to avoid it, like it has a restraining order against that number. Meanwhile, so that was for vertical. This is vertical. I'll keep the capitalization because it's a nice little trend. Then down here, however, let's show a horizontal asymptote. What do you suppose that might be? Well, this is kind of a similar thing, where the graph again approaches a function, but it seems to taper off and not quite get there, and then just keep staying a little bit away from it, as if it really doesn't want to make that last move, and instead just keeps becoming more flat. Here it becomes more straight, more vertical, more straight up, and here it becomes more horizontal. Oops, it doesn't matter, ignore that. So anyway, it becomes more and more horizontal for the horizontal asymptote. That is essentially what we see here. This is becoming more and more flat. So what we have in the context of exponential functions is we have a horizontal asymptote. And exactly what number that horizontal asymptote trends towards, what y value it trends towards, is just this c value. The horizontal asymptote approach is whatever c is equal to. So that's kind of already interesting. You will find many IB questions that ask you, could you please tell me what the horizontal asymptote of this curve is? And you'll say, certainly, of course I can. And you'll say, well, the horizontal asymptote is y, and unfortunately I don't have the symbol here, but you would have to write something like this, not equal to 1, or not equal to c, more generally. That would be the equation of the horizontal asymptote. Okay, so that's basically us having covered c. What about this b? Can we make anything of that? Is there any way we can become smarter from that understanding of what b is? Well, let's have a look at the graph again. At this time, instead of looking there, why don't we look here at the y-intercept? What's happening there? Well, let's again go into trace, and let's pick 0. Then we will actually see what it's equal to. We won't even have to do any thinking. It's equal to 3. Does 3 appear in here? It doesn't look like it. But 2 plus 1. Because let's actually run through the math of what's going on here. Well, what's going on at the x equals 0? What happens when that's true? Well, then our function is taken at 0, right? So that means that we have something like this. B times a to the 0 divided by k and then plus c. But here's the thing. It doesn't really matter what k is now because 0 divided by k is still 0. So we've got ourselves something that looks like this. B times a to the 0 plus c. But does it really matter what a is? No, because when you take something to the 0, it just becomes 1. So you have b times 1 plus c. Well, that's kind of interesting because now we can say it's just b plus c. And the thing is, like I said, it didn't matter what a or k was. That didn't matter at all. So b controls, to a degree, the x-intercept. The y-intercept, not the x-intercept. The x-intercept is controlled by b. b plus c equals y-intercept. That's already kind of cool. We now basically have two of these things explained. The only things left are this a and this k. Well, what happens with this a? What happens if we make it, say, a different kind of number? What if we were to go back in and instead of, hold on, what if instead of picking this, which we have right now, what if instead of a 1.5 we pick something like, say, 0.5? What kind of shape do you think this graph will have now? Look at that. It's changed. Let's try and put them both up at the same time. I'll just copy this to save myself some time and try to make this go a little faster. Why can't I paste? Fine. Oh, Christ. Okay. Fine. Let's just do the exact same thing. But this time we'll do 0.5 to the x divided by 2, and then finally plus 1. So here's an interesting thing. Here's an interesting little tidbit for us to look at and something for us to consider and think about. What's going on here? You actually have very, very similar looking functions to a certain degree anyway. They cross the y-intercept at the same point and they have the same horizontal asymptote. But what's different? The red one is decreasing the whole time. It's always getting smaller, whereas the blue one, it keeps rising, it keeps getting bigger. So we can say then that basically this a, this is what controls whether the graph is rising or falling. So we can say that for a less than 1, we have a decreasing graph. For a larger than 1, we have an increasing graph. Or function, if you prefer that way of thinking about it. Either way is correct. But the point is that for a larger than 1a, we're going to see growth. But for a less than 1a, we're going to see shrinkage. We're going to see it fall. We're going to see exponential decay is the word that we use, which I might also write up. So growth, increase in graph. And then decay is decrease. Okay, so that's already now another thing out of the way. The final thing to look at is what does this k do? Well, the thing about this k, this is essentially how fast it happens. You can think of it as being a kind of way to control, if we take a look at the graph here, let's try and play around with it. Let's change this one back to 1.5, but instead of having it divided by 2, let's have it be divided by 4. This one grows slower. It still grows, but it happens slower. But it also, conversely, if we have these like lower ones, it also seems to start higher. It doesn't shrink quite as quickly as we go out. That's because we have this divide by 4. We are essentially stretching the graph the bigger we make k. K can stretch the graph. So with that, we now essentially have explained almost everything there is to explain about exponentials, at least in terms of like, the sort of things that we have to know about them. And now I just need to quickly check my notes and see if there's anything that we need in addition to this. Yes, we do actually. We do need one last thing, which is that I need to show you how to actually solve equations with these. Now, so to that end, what I'm going to do is I'm going to tell you the kinds of questions that you'll often be asked to solve. For that, I think I'm going to need some more space on my lovely diagram here. So I'm going to zoom a little bit out, and then I'm going to go over here and zoom back in. Now, the kinds of questions you'll often be asked is, for example, there might be some kind of an exponential function. Maybe this exponential function has a unique look to it like this. The exponential function is something like f of x equals to 5 times, let's call it 1.3 or something like that, x divided by 4 plus 3. And then maybe the question is, when is this function equal to 25? It seems reasonable enough. What we really would have to do, right, is we would have to say, okay, let's set this equal to 25. Excuse my very, very bad handwriting. I'm sorry, but it needs must. Anyway, we are interested in when is this equal to 25. The way that we do it is we go into the calculator, and then we would go, let's have a look at these different functions. Let's just scrap this one for now. Why won't it go away? And then let's do the same with the first one, so that we have a fresh start. And then let's try and type it in. 5 times 1.3 taken to the power x divided by 4 plus 3. Now, we want to know when is this equal to 25. Well, we have a tool to do this, and this tool is one that I'm going to be using again and again and again and again and again. So if you don't get it today, you'll have another chance to get it. I promise you that. What I'm going to do is I'm going to say, okay, I want to know when it's equal to 25. Why don't I just put in a function that's equal to 25 all the time? Then all I got to do is look at this and go, well, when is this graph, this blue one, when is it the same as this red graph? It's pretty obvious. It's here where they cross. That's when they're equal to the same thing. So if I want to find that point, I can go in on the calculator and I can use analyze graph and I can use intersection. I can pick a lower bound before the point where they cross and an upper bound after they cross. And suddenly I have my answer. I have the answer here that this is equal to 25 when x is equal to what did it say? 22.6. That is, in short, the way that you would do it. Of course, you might also get another question, which is something like, what is this equal to when x is equal to 5? Well, that's also pretty easy because, again, we can just go into the calculator and we can just, instead of picking analyze, we can go into trace. Then we can simply say, well, let's let x be equal to 5 and see what the answer is. 9.94. Okay. So that's 9.94. Oops, bad choice, that one. 9.94. Now, the final thing is that sometimes they'll be really slick. They'll be a little bit tricky, and they'll say something to the tune of, when is there only half of whatever the initial thing was remaining? Well, there you have to think carefully and go, well, what is the initial thing? The initial thing is whatever the initial thing is whatever the y-intercept is equal to. So, for example, here, if we have this as a function that maybe describes, I don't know, the amount of rabbits in a hole. Rabbits being very, very well known for rapidly increasing in number. Let's start by 0 then. At 0, we see 8 rabbits. 8 rabbits to begin with. Okay. So, when is that doubled? When does this double? You pick a point, then double the y value, check the x value with the first technique. So, we have picked our point, the initial point, 0, comma y. 0, comma 8. 8 is the y value. So let's try and go in and make another graph, one that is at 16. Because that's twice as much as 8. That's when it should be doubled. Let's have a look and see what that point is. By picking f3 and f of 1, the lower bound before the intersection, as always, and then the upper bound after the intersection. It's at 14.6. So at x equals 14.6, that's when we have this kind of doubling of the value. We'll talk more about this as we go on. But an interesting consequence of this is that means that every time x goes 14.6, you actually, in principle, ought to see. Never mind. I need to be careful with that. I will hold off on that for a while, and we will mention it later. But for now, that covers nearly everything I wanted to mention. I don't think there's anything else to look at. The only thing left that I might want to talk about is the idea of the natural exponent. Natural exponent. The natural exponent is a special number that has all kinds of uses in mathematics. We don't really have the time to get into it today, and plus there are too many to mention. But if you pay attention when we start doing calculus, for example, you might notice this number come up many times. And if you are in physics or in chemistry, you will also see this number come up a lot. It's interesting because it has many unique properties that other numbers just don't have. We call this number E. And E is equal to, if I remember right, about 2.718 or something like that. There's nothing particularly fancy about it. It's just a special number that you don't need to know. You don't even need to remember what it is. All you got to know is that it's special. 2.718 E, special number. Same rules apply. Same systems apply. If you take it to, if you take this to the power of 0, it's the same as taking this to the power of 0. It's still equal to 1. It's still nothing special. It doesn't disobey any rules. It's just especially good at obeying some special rules that we haven't talked about yet. But we'll cover that sooner or later. With that in mind, I think I've covered almost everything I wanted to say during this class. So I hope that you have been able to put up with this slightly impromptu lesson, despite some difficulties here and there. And I hope that it helps you a little bit with some of the exercises you're going to have to do later. If not, I'm still available on Lectio. You can also message me on Teams, and I can try to help you as you need to, or you can talk to me next time, whatever you need to do. There will be time to get this right. Hopefully, we'll get it done.